Hello students, good evening ma. Today let me discuss about the revision of unit 2. Is it clear? Did everyone able to listen my voice? Am I audible to everyone? Yes or no? Right. So today our topic is a revision part of your unit 2. Some of the students said that they have not cleared this biasing concept. So today we have only 1 hour. So we plan to conduct a revision of unit 2 because only we have 2 topics left, which are already we have covered here. CE amplifier, single stage CE amplifier, and we also have one more topic which is multi-stage RC coupled amplifier. So single stage CE amplifier and multi-stage RC coupled amplifier is left, so that we can cover it in the next class. So today's session is this 1 hour. I wanted to take your the doubts. So I wanted to clear your doubts, as well as I want to take a revision part of your unit 2. The concepts which are not clear is biasing. So now basically what does mean by biasing is, so adding here some DC signal to that amplifier stage with that addition of DC signals. So we wanted to maintain a constant amount of voltages and a constant amount of current to be transferred with the zero signal input. Actually, we prefer, so now basically the transistor as an amplifier. Why would prefer your transistor as an amplifier is, so in order to amplify the weakest signals, so which is having the low strength in the voltage magnitude. So in those signals are applied as an input signal to the amplifier stage. So the voltage level is amplified at the output of your amplifier. If the transistor in an amplifier, we are going to utilize the component which is termed as a transistor, BJT or a bipolar junction transistor, and that must be operated under active region. So what does mean by an active region? Like your PN junction diode, we have two types of biasing, forward bias and reverse bias. But in a transistor, we would have two junctions. Now, based on the biasing of those two junctions, the transistor is operated under 3 regions of operation. First one will be the cutoff, second one will be the active, and the third one will be the saturation region. Now, so cutoff region. How to place the transistor under cutoff region? I don't want to transfer any charge carriers from emitter terminal to collector terminal. So in order to not to transfer any charge carriers from emitter region to collector region, so we are going to apply both junctions reverse bias. So when you apply both junctions which are reverse bias, there is no amount of carrier concentration is available, since our applied external biasing is 0 on both junctions. Hence both junctions are reverse bias. If those two junctions are reverse bias, no charge carrier movement takes place. So when there is no charge carrier movement, then the amount of current flow is 0. So under cutoff region, the transistor both junctions are reverse bias. Since that, so your transistor doesn't conduct. So because there is no amount of charge carriers flow from emitter to collector region, since that both junctions are reverse bias. So there is no external force, so there is no amount of carriers which are travel from emitter region to next region. I have not started my slides. Yes, this is the introduction part for your biasing. So just I'm showing your first slide. Okay, don't worry, I'll move to the next slide. So this is the part of your just BJT. So how it acts like an amplifier. Okay, right? Is it clear, everybody? Right? Yes. So next one. So in saturation. So there is a heavy amount of current flow from emitter to your collector region, since both junctions are forward bias. So there is an external force which you are applying at both the input junction and output junction. So the charge carriers will drift from emitter to base, thereafter base to collector, and will collect the output current at your collector terminal. So hence, the an enormous current is flowing under saturation region, since that transistor is acting like a on switch. So because the amount of junction voltage drop is very less, so with the saturated voltages which you are applying at the both junctions, since that so your saturated voltages are constant with a minimum amount of voltage, we can get it from your output junction of your collector to base junction. So then our collector current is multiplied, so your base current is multiplied with beta times of your IB. So then here next, so it is acting like an on switch. Now how this transistor can act like an amplifier? Only under active region or in linear region. So what does mean by linear region is, so the current is linearly varying with applied voltages. So hence here when your current is the portion where the current is linearly varying with respect to your applied voltages is known as the linear region or the active region with a factor of beta. So that region is known as the active region. Hence, so your transistor under active region is acting like an amplifier. So your none of your components cannot can act like an amplifier. Your PN junction may not act like an amplifier. Only your transistor as well as your FETs also, your field effect transistors also act like an amplifier. So, but here, in order to have a faithful amplification, now in our CE in configurations of your BJT, we just discussed about the characteristics of your each configuration. So if I apply those DC signals on your input and output junctions, if I vary my input voltage, what is my input current? And if I vary my output voltage, what is my output current with a constant amount of input current? So which yields your input characteristics and output characteristics of your transistor. So those are configurations, characteristics are discussed with the DC application of your signals. So we have done with the DC analysis of the circuits only in configuration. Now let me move to the AC analysis. So now in an AC analysis, not only we are applying the DC signal, we we have to apply in order to amplify the weakest signal, we have to add some source signal as an input, an AC signal, alternating current signal as an AC signal, so is applied as an input. So now here at the base of your transistor, then only, so we, no, if I apply your AC signal as an input, it can't function like an amplifier. The transistor should operate in a linear region or in active region. Then only it can amplify the weakest signal. So we'll get the amplified output of your transistor. We collect your amplified voltage signals at the output of your collector or your collector term of your transistor. Now, let me introduce. So, what does mean by biasing? So, this biasing is, so we are operating the transistor under active region. So, in order to operate that transistor under active region, so we have to apply some magnitude of your DC signals on your transistor, which can maintain a constant amount of voltages and a fixed amount of current which can pass through the transistor. Hence, here the biasing is nothing but application of DC voltages to establish a fixed level of current as well as the voltage. So that fixed level of current is known as your quiescent values. The fixed levels of your currents and voltages are known as the quiescent values. So which are denoted with VCQ as well as ICQ. And these are not due to your applied AC signal. Only these quiescent values are due to the application of the DC signal, and we are applying the DC signals to the transistor to operate your transistor under active region, as well as in order to obtain the the distortion less output at the collector terminal. So here we have to apply some amount of DC signal with the additional circuitry. So that additional circuitry, why we require to add to our transistor, so that we are going to deal in our next slides. So now this analysis of design of any transistor amplifier. So would have to be no, we would have to have a knowledge of both AC response as well as the DC response. Now the DC response of or a transistor, we have concluded that in configurations. Now we're going to analyze now the AC response of the system. So for a faithful amplification, in addition with this DC signal, how it amplifies that AC signal voltage level to a required strength, or how it increases the voltage signal strength, that we are going to deal now. So now it is having some, so your output would have a DC portion, as well as it also have a AC portion. Now during the design stage, so the choice of your parameters for the required stability, or for the required amount of your AC levels, or the small signal is amplified to the required voltage level. So we have to maintain some parameters. So it has to be maintained. The quiescent point must be maintained exactly at the center of the load line. So in order to maintain that, we require some parameters, and those, if I add those parameters, may they affected by your external parameters of like a thermal, they might be thermal sensitive materials, or some aging factors, some parameters, external parameters are also added with that. So if those are added, so then there is a chance of that point, that fixed amount of currents may change, or the fixed amount of voltages may change due to the DC DC voltages. So now in order to stabilize those points, or the DC voltage levels, or to have the faithful amplification of an AC signal after applying an AC signal. So what are the measures we have to take, that we will cover it in the stability of the transistor. Right now, in next slide, we are going to deal with, one second, Anna. Is it clear till this? So what is the need of biasing? Everybody? Are you able to understand now? What is the importance of biasing? I'm asking a question. Please respond, Nana. Are you able to understand now? What is the importance of biasing? Yes? Right. Now, I'll move to the next slide. Now, so this is the purpose of your DC biasing, which is needed in an amplifier circuit. The first one is in order to turn on your transistor in on state. So the second one is so to place the transistor in a region where its characteristics are linear. So your device is behaves like a linear. Your current is increasing in a linear fashion in the active region. Hence, we require the DC biasing. Next, the third point is a proper biasing circuit which operates in linear region and the circuit is centered at a Q point or your quiescent point. So a proper biasing or a proper applied DC voltages can manage the amount of quiescent values on a DC load line which maintain that quiescent point exactly at the center of the active region. So now if I move that quiescent point anywhere towards your saturation region or towards your cutoff region, what will happen? That we'll see in the next slide. Next, if we are providing an improper biasing. So, for example, applied voltages or your extra additional circuitry, what you require for a biasing, if we maintain an improper biasing circuit, it can cause the distortion in the output signal. So now, so in order to avoid that distortions at the output or to some part of the output signal or your if you apply a sinusoidal signal, my output of the amplifier must be in the nature of sinusoidal. In the same shape, I have to get it at the output. In addition, with that amplified voltage levels, my shape of the output should not vary. It should be exactly as same as like your input. Only the strength of the voltage level must be amplified, not the shape of the waveform should not vary at the output. So in order to maintain that, so we require the proper biasing circuitry. So these are the 2 points. If we doesn't have a proper biasing, we can experience a distortion in the output signal as well as the output signal is limited or some part of the output signal might clipped. Okay, hence we lost the signal strength. The total signal strength of the output may be lost if some part of the output is clipped or if it is limited. Hence, we require a proper biasing circuit or a proper biasing method. Right. So now, in order to describe that, so we require the basic important relationships of your transistor. As we already know that amount of current which is emitted from the emitter region is the sum of collector current as well as the base current. And the amplification factor is the ratio of output current to the input current. Now, we are taking the common emitter configuration or a common emitter as an amplifier. Since the characteristics of common emitter amplifier are moderate in all the characteristics. It is having the highest input resistance, the lowest output resistance, the moderate output voltage gain, the moderate output current gain. So now the current gain as well as the voltage gains of your transistor CE amplifier, common emitter amplifier are moderate. Hence, the generalized as an generalized amplifier, you can take your CE configuration as an amplifier. Right. Now, so now the next expression what we have is IE, the emitter current. How we got this beta plus 1 times of IB is we just replace your IC with the beta IB. If I replace IC with the beta IB, so if I replace your IC with beta IB, then we have IE is equal to I beta plus 1 times of IB. Now, if I neglect this 1, so it is equal to beta IB, where beta IB is equal to IC. Hence, so amount of base current is very less since the base width is very narrower compared to your all the remaining two region, which is very less. The region of your width of the base is very less, as well as we are in your active region, we are providing reverse bias from your output junction at your output junction and a forward bias at your input junction. If I am providing a reverse bias at output junction, the depletion layer width is more. This is the most important point. So as already I told you in the session of your biasing, so the width of the depletion layer width is more penetrated into the lightly doped region. Now in a transistor, the lightly doped region is base. Hence, so the effective width of your base region is very less. So hence the amount of base current is negligible if I compare the amount of emitter current with your collector current. Hence here the amount of emitter current is approximated to the collector current. Now, as we know that our collector to emitter voltage is, if I apply a KVL in the transistor, amount of collector voltage is equal to the amount of base to emitter junction voltage plus of your collector to base junction voltage. Now, if I require the output voltage, then it will be the VCB, the collector to base junction voltage, is equal to VCE minus of VBE. VCE minus of VB. So these are the most important basic relationships in your transistor. The quiescent values of your, in order to obtain your quiescent values of your constant amount of current, output current and quiescent output voltage VCQ, we require these relations. Right. Next, transistor biasing. The basic function of transistor is amplification. Next, the process of raising the strength of a weak signal without any change in its general shape is referred as a faithful amplification. If you are if you are providing a improper biasing, then you doesn't have that amplification, faithful amplification. So your output might be distorted. So due to that, we have the power loss. So hence, so we require a proper passing for a faithful amplification, as well as it can amplify the weakest signals. So it can amplify the lowest magnitude voltage levels. Next, for a faithful amplification, the essential criteria is here is emitter to base junction is forward bias, collector to base junction is reverse, input junction is forward bias, your output junction is reverse bias, as well as you have to maintain a proper zero signal collector current. So what does mean by a proper zero signal collector current is, so if I am not applying your AC signal, so due to the applied DC biasing voltages, we have to maintain a constant amount of a DC current as well as the DC output voltages on a amplifier stage. So with a zero input signal of AC, so with the additional DC signal, if I maintain a constant amount of quiescent values of here, quiescent values of current and voltages. Then, so your transistor can amplify your applied AC signals without distortion. So we require input junction must be forward bias, output junction must be reverse bias, as well as we have to maintain a proper zero signal collector current. What does mean by zero signal collector current? So with the AC signal, with the input signal, nothing but your AC signal. If it is zero, we are not applying any AC signal, then we should maintain some amount of DC currents and some amount of DC voltages on a transistor due to the biasing, the additional biasing. So with that, the operating point is fixed at your center of the load line, and then we apply the AC signal. When I apply the AC signal, then that weakest signal is superimposed on your DC voltages and the DC currents. So then we would have that faithful amplification. So your shape of the waveform will be maintained as it is like your input waveform with the amplified voltage. The signal strength is amplified at the output. Okay, is it clear everybody? Is it clear everybody? Yes. Is it clear everyone? Next, I'll move to the next slide. Till this point, is it clear everybody or not? Everyone? Is it clear, Nana? Okay, right. Next, I'll move to your next slide. Okay, Redma. Next. So these are the output characteristics of your transistor, where I have here, just look it out here on common emitter configuration I took here. So output characteristics of your common emitter configuration. So I'm taking on x-axis your output voltage, y-axis I'm taking your output current. And this is the portion of saturation region, where this is the portion of your cutoff region where the current is, the amount of collector current is IC is 0, that portion is known as your cutoff region. So here, whereas here this portion is known as your saturation region because of the heavy amount of current flow. So without your VCE, so with VCE 0 itself, we are having your saturation, we are having a highest amount of collector. So how could it having that highest amount of current flow with VC is 0? It doesn't depend on your collector to emitter voltage, because so when your output junction is reverse bias. So now we are moving towards your negative voltages. So when I'm moving towards your left side, so then our output voltage VCE become positive, sorry, negative. When it become negative, so your base to collector junction voltage might be forward bias with the negative voltages. When your output junction is forward biased and your input junction is forward biased, then your transistor is operated under saturation. So your collector to whenever collector to emitter junction voltage leads to negative, your transistor is operated under saturation region. Since the base to collector junction become forward bias, because in an NPN transistor, my collector need the negative voltage to operate in forward bias region. So forward bias. So when I apply a negative voltage to that collector terminal, so obviously your base to collector junction become forward, as well as your input junction is also forward. Your transistor operated under saturation. So heavy amount of current is flowing through that junction. So with the IB 80 microamp, you would have the maximum amount of current flow might be in the range of 25 milliamps. So with the IB 70 microamp base to emitter junction, if we are a forward bias, so with the IB 70 microamp, you would have your 20 milliamp of current. Now, when I'm moving towards my VCE, which is positive, from 0 to positive, so your base to collector junction become reverse bias. So hence, your transistor is operated under active region. When it is operated under active region, simply it depends on the current gain of the amplifier, which is IC is now depends on your beta times of your IB. Since my base current in your sorry, since my current input current in my common emitter configuration is base current. So with a fixed amount of current, so you would have here, example, if it is 20 microamp, we have here 5, 5 milliamp of IC, then obviously it is increasing linearly with the beta factor. So hence here, so now we have to maintain, now we have to draw a DC load line on this output characters. How to draw that DC load line is by taking the output characteristics. So now if I apply the KVL on output loop, then it will be equal to VCC minus of voltage drop across here. Resistor is ICRC minus of VCE. So VCE is equal to 0. This is the actual KVL in a common emitter configuration. Now, in order to draw the DC load line, so now we require 2 points on that line. So where one point I will take it on a x-axis, the other point I will take it on a y-axis. So I'll mention that as a node A on your y-axis and node B on your x-axis. So now, in order to maintain that, so here VCE must be 0. Hence, now when VC becomes 0, so we have the maximum amount of output current. IC is, when IC is 0, then VCE become is equal to quiescent value of the quiescent values we are just finding. So the quiescent values are nothing but your, these are nothing but your operating voltages, and these operating voltages are due to the applied DC bias. So this is the maximum amount of the node. So node B, x coordinate is VCC by RC, and y coordinate is here IC is 0. So when IC is 0, we'll have the node B, which is equal to VCC by RC, comma 0. So now let I'm taking this as VCC by RC maximum, which is node B. Next, one more point I need on y-axis, which I wanted to draw a DC load line, and that node would also have a y coordinate as well as your x coordinate. So what is the y coordinate value is here? In order to find that here the x coordinate value become 0, hence because of VC is 0, when VC is 0, so amount of maximum current is IC become VCC by RC. Sorry ma. When IC is 0, VC is equal to VCC minus of ICRC minus VCE is equal to 0. Since IC is 0, then VC is equal to VCC. Hence node B is equal to VCC comma 0. Next, here in order to find node A, the x coordinate value is 0. Hence voltage, collector to emitter voltage is 0. Hence maximum amount of current flow IC max is equal to VCC divided by RC. Hence node A I can obtain as the x coordinate value is 0 and the y coordinate maximum value is VCC divided by RC. So one point on y-axis, now we have node A as 0 comma IC maximum or VCC by RC. So if I draw the line, one second. If I draw the line which joins your A and B, so then this is known as DC load line. How we are obtaining this load line is by just substituting the values of collector to operating voltages as well as your operating current. So now in order to obtain this voltage, so we have taken the current, collector current is 0, then we'll get VCE is equal to VCC. So whereas here, when I wanted to get your maximum collector current, then I already said that if collector current is 0, then collector to emitter voltage approximately equal to VCC. Since we doesn't have any drop across your collector resistance. So when it doesn't have, if it doesn't have any current flow through the collector resistor, then there is no voltage drop. Hence, we can collect the whole amount of voltage what you apply on your collector terminal exactly, which is VCC. Hence here, collector to emitter voltage is VCC. So we have here VCC comma when IC become 0. Next. So now we need to find your maximum collector current, the maximum amount of current, collector current which you can transfer through the transistor with a DC voltage by just substituting your VCE. Since, so if I have a heavy amount of current flow through a RC, then the total amount of voltage will drop across your RC itself. Then amount of voltage collected at your collector to emitter become 0. So if total amount of voltage what you apply on collector to base junction, which is VCC, will drop across here resistor RC, since that maximum amount of current is flowing through the resistor, collector resistor RC. So what is that maximum amount of collector current is equal to, it is the ratio of VCC divided by RC. So this is the maximum amount of allowed collector current due to the biasing, which is VCC by RC. and this is the maximum amount of quiescent value of voltage what you can allow through that transistor, which is equal to the magnitude of VCC. So now using your specifications or the data sheets. So on each transistor we have a data sheet. So the allowed quiescent values we have they will mention that. So we should not exceed these values beyond these values of maximum levels which have VCE is VCC as well as here IC become VCC by RC. Now the DC load line can be drawn with this two nodes from A to B. One I2 can y-axis, another I2 on your x-axis by just taking your collector current 0, whereas here the collector to emitter voltage I have took it as a 0. Nothing but here it is a extreme end of your saturation. So hence collector to emitter voltage is 0, maximum amount of current. Whereas here this node B we are taking by considering the point which is in cutoff region where no amount of current flow, collector there is no amount of current flow means so your both junctions are of reverse bias. When both junctions are reverse bias, amount of current is 0, hence amount of voltage is approximately equal to VCC because there is no current through the RC, hence VCE is equal to VCC. Now, the thing is here, so this is about your actual basic concept how to draw the DC load line or how to do the DC analysis and how to find so what is the operating voltages. So only how much of voltage you have to apply as a base to collector junction as well as at the input base to emitter junction. So magnitudes of maximum and minimum values. So now we are going to discuss about in the next slide. So where we have to keep the operating point. As I already mentioned here, some points which are here which I have denoted with a B, which I have denoted with a D, as well as which I have denoted with the C. So now your operating point might be placed at anywhere in the linear region. So if I place at anywhere in the linear region, so what happens next? So that we have to discuss. Okay, is it clear, everybody? Yes. Is it clear? Everyone? Is it clear, Nana? Till this slide? Is it clear? Can I move to the next slide? Yes. Okay, right. Next. Now, see here. So I can place my operating point. So the operating point. So due to the applied DC voltages, so your operating point might be at anywhere in the linear region, and that depends on the magnitudes of VCC and the components which you connected in the biasing circuit. So it depends on the currents as well as it depends on the voltage. And the voltages depends on your base to emitter junction voltage as DC voltage as well as base to collector junction voltage. Next, the currents, the DC currents depends on your the base current, emitter current as well as your collector current. Now, so here, so I can put my operating point at any point at my linear region. So throughout this part, this region is known as your linear region where your current is increasing. So now if I put my operating point at this saturation, just look at out the second image you have. Here we took your Q point. I've mentioned it as in the first image we mentioned, just look this. So I'm just highlighting this. So this one. So this is your Q point exactly. So we have drawn a DC load line, and this DC load line is drawn based on the maximum amount of your current flow due to your DC voltages and the DC currents. So this is the maximum amount of DC current you can allow in a transistor, and this is the maximum amount of DC voltage you can allow in a transistor. So based on this, we have this node A and node B. Now the first image I said, so I've placed my operating voltage or the operating point exactly at the center of this DC load line. Whereas here, the second image, I've placed the operating point at near the saturation region, near the saturation region. Whereas in the third image, I've placed my operating point exactly at the where I placed it at a cutoff region. So, so almost this point, and whereas this point, so it is near to cutoff, whereas here it is near to saturation, whereas it is exactly at the center of the DC load line. So now if I put my operating point, so this operating point is based on your applied DC voltages, right? So now on this operating voltages, VCQ and ICQ, your input is superimposing. Your input is your weakest input signal is superimposing on DC signal. Then only we have the faithful amplification. So your voltage magnitude is raised due to the applied DC voltages or the DC operating voltages. Then only it is amplified. Otherwise, it can't be amplified to that required voltage strength. So it is as like your transparent latch. So you could have your the same amount of input is transferred to the output with the same signal strength. So the weak signal is transferred as like here with the same signal strength like a transparent latch. Whereas in an amplifier with the additional biasing. So biasing is addition of DC voltages and DC currents. So these additional DC voltages and DC currents can manage your transistor which is operated under active region. So with this additional DC currents and DC voltages, your applied AC input signal is amplified at the output with a beta times. Your current is amplified with a beta times. Okay, and the voltage signal strength is also amplified. Right. So now if I put your operating point near saturation, then at the output, this is your input where I've just shown the weakest signal, and this is on the perpendicular line. So we have drawn the output. So our CE is having a 180 degrees phase shift. For the positive cycle of input, you have the negative cycle of output. For the negative cycle of input, you have the positive cycle of output. So 180 degrees. So the output is out of phase with your input. So like that also we can say output always out of phase with your input. What does it mean? It means so there is a phase difference of 180 degrees. So for a positive cycle of input, we are getting a amplified negative cycle, whereas a negative cycle of input, where if we are applying as an input, we will get a output voltage which is positive because now, so just to see here, now we are taking the voltage here. So VCE is a collector to emitter voltage which is equal to VCC minus of ICRC. This is our output voltage in a common emitter amplifier. So if IC is increasing, VCC is fixed, then for a positive cycle of input, you are getting negative cycle of output. For a negative cycle of input, you are getting a negative amount of current which become a positive voltage. So like this, we'll have your 180 degrees phase shift at the output of your CE amplifier. Now, so now here, but here for the positive cycle, because of this DC biasing voltage is exactly near to the saturation, some part of it, this I have marked with the dashed lines. Here I have marked with the dashed lines. So this part of the signal we are not getting at the output. Our output is now which is clipped. So your negative cycle of the output is clipped because I applied a positive cycle which is above the saturation. So hence some part of the output signal is missing here. So we have experienced a clipped output state or the some part of the signal at the output, right? Whereas here negative input signal because it is operated below your saturation and near to the linear region, hence it is faithfully amplified. So the complete cycle of the negative cycle is transferred, but the positive cycle of your output is, sorry, for the positive cycle of input, you are getting a negative cycle. So negative cycle of output is clipped. So a distorted. Now for a faithful amplification, if my input is sinusoidal, I have to get the sinusoidal output. Whereas now here, this part we are not getting at the output. So we are getting like this, like a clipped output. Sorry, 1 second, Nana. We are getting, for the positive cycle, we are getting a negative cycle of input. Hence here, so we are getting like this, a portion of output is clipped and the negative cycle of output, we are getting the amplified output. So this is your input, whereas this is your output, what you are getting at the amplifier. So positive cycle clipped here, a clipped portion we got it. There's negative cycle, it doesn't have any clipping. So now, hence, some part of the signal is lost in the output of your transistor. If I'm using as an amplifier and the operating point is near to the saturation. So in order to avoid this, let I move to your Q point, which is exactly at the center of the DC load line. Right. Next case, so if your operating point, it might be in the linear region, but near to cutoff region, if it is there, so then the opposite one will be done like the above case. So if it is at saturation, we have experienced a clipping at their negative cycle of the output, whereas here for the positive cycle of the output, so we have experiencing this clipping. So like this, the distorted output we are experiencing in your transistor amplifier if your operating point, the operating point depends on your applied DC voltage magnitudes and DC due to DC voltages we have some currents. So due to that DC operating voltages and currents, so your applied external AC signals are distorted at the output. So there is a power loss. So in order to obtain the distortionless output, so we have to maintain the quiescent point, so which is known as the VCEQ and ICQ. So quiescent points are nothing but operating voltages due to the external DC signal, DC bias. So VC, so this is called VCQ and ICQ are the quiescent values or operating voltages, right? So what is VCQ? Exactly, it is exactly at the midway of this x-axis, and it is also at the midway of y-axis on your y-axis. Hence, VCQ is equal to, this is the end of the node B, which is magnitude of VC is equal to VCC. Hence, VCQ is now it is equal to VCC divided by 2. Whereas ICQ is equal to, now we have here ICQ is equal to IC divided by RC, right? So instead of IC maximum, we have here IC into 2 into RC. So exactly half of the maximum collector current as well as the maximum collector to emitter voltage which yields your QCN value. So VCC by 2 as well as your ICQ which is equal to IC by 2RC. Is it clear everybody? Yes. Is it clear everyone? I'm just waiting for your response, but none of them are responding. Okay. Is it clear, Nana? Ah, okay, ma. Then, is it clear, everybody, right? Yes. Now, I'll move to your next slide. So, so this is the importance or the need of the biasing. Next, we will move to the types of biasing. How many types of biasing? So, the extra additional circuitry what you added for the biasing network is biasing, right? So how many types of biasings are available? So there are five types of biasing techniques are available. That first one will be, one second now. Is it clear, Nana? Right. Am I audible to everyone, right? So there are five types of biasing techniques are available. So now in that five types of biasing, we have the most popular one is here self-biasing or voltage divider biasing technique. So first technique is fixed biasing technique. Second technique is your collector to base bias. Third technique is your self bias or voltage divider bias. And fourth one will be your emitter bias. And last one will be the base bias with the collector and emitter feedback. So in our syllabus only we have self bias, but before we are moving to the self bias, so let me first analyze what does mean by a fixed bias. What are the advantages and disadvantages of fixed bias technique? Why we move to a self bias? Why it is most popular than your other techniques? So that we are going to learn now. Now, next, fixed biasing. So what does it mean by fixed biasing technique? So now in fixed biasing technique, let I'm taking two fixed voltage sources, or you could also take one. Fixed biasing technique. So you could take two voltage sources. One is connected at collector, the other one you can connect it at the base. Now in our circuit, I took only one common source which I have connected VCC. Actually, your CE amplifier would have only VCC is connected to collector resistor, but in fixed bias circuit, what we are doing is we have taken a RB resistor, base resistor. Let me call this as a base resistor RB. So this base resistor RB is coupled with a common source of VCC to the base of your transistor. So hence, so VCC is coupled through RB to the base of your transistor, as well as this VCC is coupled to the collector terminal of your transistor through a resistor RC. So now base to emitter junction must be forward bias, and base to collector junction is reverse bias. So the base to emitter junction is forward bias with the VCC RB, since My base is P type and my collector is N type. So base to emitter junction, as I connected your emitter to ground. So with a VCC signal where positive terminal of VCC is coupled to RB and that is connected to the base where it is a P-type material. Hence, we forward bias with respect to the common terminal emitter. So input junction is forward bias, whereas output junction is revised with the common VCC signal with the VCC and through your resistor RC connector resistor RC be coupled to the collector terminal with respect to the base junction base or output junction. So VCC is positive where collector terminal is N-type material. So we connected a positive voltage to the N-type material which leads to the reverse bias of your output junction. Hence your transistor which is in common emitter configuration is operated under linear region or it is operated under active region. So now in this fixed bias, so we connected RB, right? So now in order to analyze this, so now in order to analyze this, what we have to do is we also connected an extra components. What are those extra components? In order to act like an amplifier, we have to connect the coupling capacitors. So C1, C2. These are the coupling capacitors. So this coupling capacitor are added in order to apply the AC input signal to the base. So in order to amplify this weakest AC signal, we have to couple through a coupling capacitor to the base of your transistor. Whereas here, to collect your output, amplified AC output signal, so we have also connected one more coupling capacitor at your collector terminal. Now, in order to analyze this fixed bias circuit, we have two steps to be followed. First, it has to be function like an amplifier. Hence, we connected the coupling capacitor. But for the DC analysis purpose, so in order to find your the QC and the values, will those depends on your any parameter or not? So are they stabilized or not? Will that operating point is moved due to your any parameter changes or not? Not to check that, so we have to apply the DC analysis. So in order to do the AC analysis, our second step is we have to locate the two main loops of your transistor. So now in this transistor, the first loop will be the base to emitter junction loop, which is input loop. The second loop will be collector to base junction or your output loop. As I'm taking your emitter as a common term, so hence I have mentioned here it is a collector to emitter loop or your output, right? So now next I will move to your next slide. So in order to analyze the DC analysis, we are doing the DC analysis. So if I'm doing the DC analysis, then these two capacitors must be shorted. So in order to act like an amplifier, so we have to connect this capacitor. But now we are doing the DC analysis. If I'm doing the DC analysis, so what does mean by DC analysis is only with the applied VC signal, will that operating point is fixed at exactly at the DC load line midpoint, or will they available at anywhere at your linear region below the cutoff or your above cutoff, or do you have any distortions? In order to analyze that or to find that, so we have to do the DC analysis. So when you are doing DC analysis, these capacitors must be open circuit. Since your why you are open circuiting your capacitors, since my reactance offered by the capacitor is XC is equal to 1 by 2 pi FC. As I am taking the capacitor value is very less, and the frequency of operation, yeah, I'm just finding the response of the transistor for the applied DC signal, not for the AC signal. So hence, in a DC analysis, while I'm doing your DC analysis, remove your AC signal or just you just disconnect your AC input signal and short your capacitor, sorry, open circuit your capacitor, because the frequency of DC signal is zero, reactance offered by the capacitor for the DC signals F is equal to zero, frequency of DC signal is zero. Now 1 by 2 pi fc, so become 1 by 0 is equal to infinite. So if the capacitor reactance is infinite, means the reactance which is offered by the capacitor, if it is infinite, it simply act like an open circuit. So if I remove your, so here open circuit, if I place it at your coupling capacitor C1 and C2, then directly your VCC is coupled to the base of your transistor through your resistor RB, as well as here RC only, right? So now next thing is here we have to find, so what is the base current, what is the amount of collector, will that collector current due to the DC voltages depends on your beta value, will it depends on your base to emitter junction voltages, will it depends on your temperature. These all the things we have to find in order to find the stability of the biasing circuit. To find your stability of the biasing circuit, we have to do the DC analysis. So now why you're doing the DC analysis means, so in order to find that QCN point, it may not, so it should not vary the DC biasing conditions, as well as should not affected by your base to emitter junction voltage changes, as well as it should not affected by the current gain changes, and this current gain changes is occurred due to the parameter changes. That parameter changes will occur due to the additional circuitry what you needed to connect that DC signal. Here we connected that VCC through RB. So hence, if there is any changes in the RB, if I remove the RB resistor with another resistor value, if I remove, for example, my transistor is burned out. Now I just wanted to replace the transistor with the same type of transistor. But we know that, so no two components are having the same similar characters, so it have some tolerance, so no two components are having the ideal characteristics. Hence, so due to that mismatch, you might experience a distorted or a movement in the DC or operating point on the load line. Hence, okay, right, now the time of right. So next I'll continue this part of fixed biasing in the next session. So in the next session also we're going to do the revision part. On Thursday, let I wind up your session. So on Thursday we doesn't have any quiz session. So sorry, not Thursday, Wednesday. Wednesday we doesn't have. So I'm going to review your second unit. So on Thursday I wanted to wind up. So on that day you have the quiz. Okay. So for today's session, so this is part of the fixed biasing analysis. Let I continue this in the next class. Okay. For today, I'll wind up. Okay. Thank you, ma.